And the best part has been saved for last for our series finale. My favorite part to the basics of astro tools is also the most important tool in astronomy, and that's the study of light or spectroscopy. Without ever even visiting a light source, I can identify its origin based on the properties of light it emits. And without ever even visiting the matter that warped and redirected light and its properties, I can identify the type of matter and interaction that took place for the change to occur. Today, I'm going to show you how to search for and identify the fingerprints of light. We know how to break light up to study its properties, and we called this separation a spectrum for light, or the electromagnetic spectrum. Sometimes a light spectrum from a particular light source will exhibit bright or dark lines that might look something like this. But what if we wanted to know easily how much energy is just in the red wavelength of light compared to how much energy is just in the purple wavelength of light? To easily extract quantities like this, astronomers will plot instead the light intensity by its wavelength. And in this way, we can see exactly how much energy in each wavelength of light there is. And these bright and dark lines that we saw in the spectrum are now being displayed as spikes or dips in the plot, which are corresponding to excesses of energy at that wavelength, or an absence of energy at that wavelength.
We can study all different types of spectra using diffraction gratings, which are basically prisms that are designed to separate light into its spectrum. There are three basic types of spectra when studying light. When a source produces a light spectrum with no features, such as no dark or bright lines, nor spikes or dips, it is called a continuous spectrum. The visible light spectrum generated by an incandescent light bulb, for instance, is a rainbow, and it shows a continuous transition from one color of light to the next, so it is a continuous spectrum. When a light spectrum shows very bright lines appearing at specific wavelengths, it is a type of emission spectrum. For instance, clouds of hot gas can emit very bright lines in their spectra. The light emitted is determined by the properties of the cloud, such as its temperature and the chemical composition. A light spectrum that is identified with low intensity or dark lines or dips at specific wavelengths is an absorption line spectrum. In this case, a light source must be interacting with some kind of matter, such as a gas cloud, and this gas cloud is absorbing only some of the light, and that corresponds to these dips or dark lines in the spectrum. The light absorbed by the matter is determined by the cloud's chemical composition and temperature.
Okay, great. We can now identify the unique features of light by studying its spectrum. But how exactly do we identify the type of light source or matter it may be interacting with using these features? This requires us to go back to our discussion on energy levels. Each emission or absorption line corresponds to a specific atom, ion, or molecule's bound electrons gaining or losing energy in the form of light. Remember that energy levels of bound electrons are discrete or quantized, which means that the electron requires a specific amount of energy to move within the levels.
This means that an emission line is the energy that has been released or lost by a particular atom, ion, or molecule whose bound electron left an excited state for a lower energy level, and it lost energy by emitting light in the process. This process is pretty common because the electron wants to remain in the ground state. In the hydrogen atom, if an excited electron in the third energy level releases exactly 656.3 nanometers of energy, it will move down one energy level while emitting a photon with exactly 656.3 nanometers of light. This corresponds to visible red light. We see this as a bright red emission line. The amount of energy required is unique to each energy level of an atom, and is doubly unique to each individual atom. For the hydrogen atom, we notice how moving between varying energy levels requires varying amounts of energy. What would it look like for helium? What about neon? What about sodium? We see how each emission line spectrum differs, all because of the unique energy levels of the bound electrons. The same idea is behind absorption lines in light spectra. Suppose we place a light bulb behind some of this hydrogen gas that we have been looking at. The light bulb by itself will have a spectrum that looks like a rainbow, but if hydrogen gets in between, it could look like an inverted version of the hydrogen emission spectrum, and that's because it is. An absorption line spectrum describes the absence of light at specific energy or wavelengths because that light has been absorbed by something. What is absorbing that light is determined by the absorption lines. We see that each absorption line corresponds with the exact energy needed for a bound electron in the hydrogen atom to be excited and ascend in energy. That must mean that hydrogen is absorbing light that was originally emitted by the light bulb.
With every atom, molecule, and ion each having their own unique allowed energy levels and thus unique spectra, we can now identify light sources by studying their spectral features without ever even leaving our seats. But wait, there's more.
Consider an object that absorbs almost every photon that it runs into and traps each of those photons within it, making it very difficult to escape. The photons will bounce around randomly in the object, so that by the time the photons do escape the object, it has randomized energy from exchanging energy while bouncing around inside the box. If we were to look at all the photons escaping from the object by their corresponding wavelength, we would see a wide spread from this randomization. Look familiar? It's a type of continuous spectra. These spectra only depend on one thing, the original object's temperature. The photons literally ended up escaping with energy that matched the energy of the particles that make up the object. This temperature dependence is the definition of thermal radiation. There are two laws specific to thermal radiation. The first law we also call the Stefan-Boltzmann law, and this means that hotter objects emit more light per square meter of the surface at all wavelengths than cooler objects. And then the second law we also call Wien's law, and this describes how hotter objects emit photons that have higher average energy than cooler objects. We can see both of these laws when we think about an open flame. The brighter the flame, the hotter it is. And this demonstrates Law 1, or the Stefan-Boltzmann law. And the hottest part of the flame corresponds to the base of the flame, where it appears blue, which is the shortest wavelength. So that must mean it has the highest temperature. The coolest part of the flame, though still really hot, which is the tip, and that appears orange, which must mean it has a longer wavelength and thus lower temperature. And that is Wien's law, or Law 2.
These laws are exactly why the stars in our night sky have varying colors. Their colors are indicating their temperature. Betelgeuse is a very bright and yellow star compared to its nearby night sky companion Rigel, who is also very bright but shines white or even bluish some nights. This must mean that Rigel is much hotter than Betelgeuse.
Light can tell us even more than just the temperature of the emitting object. Light can also tell us the speed of these distant objects through the Doppler effect. You may have already run into this phenomenon before with sound waves. For example, the sound of a train whistle as a train passes by. If the train is stationary on the track and whistles, the sound just has a constant pitch, right? No matter where I stand, the whistle is going to sound the same. But now the train starts to move away from us. Did you hear that drop in pitch? The frequency of the train whistle is decreasing, which means the sound wave is being stretched as the source of the sound moves away. What happens if the train is instead moving towards us? Will I hear a drop in the whistle's pitch or an increase? Well, the opposite will happen. The wavelength of the sound gets squished as the train is getting closer now. So now the sound wave has a higher pitch than before as it approaches us. The Doppler effect is the reasoning behind the changing pitch of sounds as things move towards or away from us. And this effect applies to any wave, even light waves. If a star or gas cloud is moving towards us, the light emitted from the object will be measured with a higher frequency, shorter wavelength, and thus higher energy than the true light that left the object. Because shorter wavelengths of visible light are bluer, the Doppler shift wave that we observed from this approaching light source is blue shifted. If the light source is instead moving away from us, where we observe the light waves at longer wavelengths, frequency, and hence lower energy, then the fleeing light source is red shifted. Even when the light waves are Doppler shifted outside of the visible light spectrum, we adopt the same terminology. So even if a star's ultraviolet spectrum is actually observed in the visible light spectrum due to the star moving away from us, we still call this spectrum red-shifted to indicate that the spectrum is observed at lower energies than the original wavelength's energy.
So how exactly can we tell that the light we are seeing is not the true light emitted? Well, we know what spectra from elements like hydrogen, helium, sodium, and so on look like. So if any of those elements are present in a Doppler shifted spectrum, all we have to do is look for those spectral features. And if they're Doppler shifted, all we have to do is compare that to what their spectral features look like when that element is not moving, when it's stationary, when it's at rest. And in this way, we can measure exactly how blue or red shifted an observed spectrum is from its actual spectrum at rest. We just covered the most important tool in astronomy, the study of light, or spectroscopy. With spectroscopy, we can identify the temperature, composition, speed, and direction of motion simply by studying the light emitted by the most distant objects in the universe. Now that we have our toolbox of basic astronomy, we conclude the second series to On Planet 9. But bring your astronomy toolbox with you in Season 2. You'll need it for the portals of discovery. See ya!